So users will often capitalize words simply for emphasis, or they'll just leave the whole message lowercase. And this is particularly challenging for this named entity recognition task, which is to find all the people, locations, and organizations in tweets. And in Newswire, at least, named entity recognizers rely really heavily on capitalization features, which in Twitter are just really unreliable. OK, so finally, tweets have this really unique grammar. So for example, users will often drop personal pronouns, assuming that the subject of the sentence refers to the speaker. And you just don't see these same kind of sentences in news articles. So it's kind of a different domain. OK, so at this point, you might be wondering, how do off-the-shelf NLP tools perform when we just take them and apply them to Twitter? And so the answer is they do actually pretty poorly. So this is just one example. So here the part-of-speech tagger misclassified the word yes as a proper noun, which is a pretty big mistake. I think you can kind of see why it is. It's this funny spelling, so it's probably out of vocabulary, and it's also capitalized. OK, so then the noun phrase chunker here thinks that its official Nintendo is a noun phrase, which is a pretty big mistake. And then the named entity recognizer missegments America as a location, whereas if you look carefully, you'll notice that it really should have gotten North America. OK, and so I'm not even highlighting all the errors that are being made here. But the point is that Twitter just has this noisy and unique style, which tools designed to work on edited text like Newswire just were never meant to handle. OK, so to address this, I've rebuilt an NLP pipeline, which is tuned to work specifically on this noisy Twitter data. And for the most part, we're taking a supervised learning approach here. And so I think there's a lot of interesting work on unsupervised learning for syntax and NLP. But for the most part, the supervised learning approaches perform a lot better. And so I just want to point out that we're really trying to take a practical approach here to get something up and running on top of Twitter. So that's really what's motivating our approach to processing syntax here. We're doing some kind of semi-supervised stuff as well, but I'm not going to go into the details here. I think there is actually a lot of room for interesting work to be done on unsupervised learning for these more semantic level tasks, like I'll get to a bit later in the talk. So we've done some work on weakly supervised named entity categorization, classifying events, and also sort of unsupervised and semi-supervised relation extraction. OK, so here I'm just showing a quick summary of the performance of our NLP tools we've adapted to Twitter compared against off-the-shelf state-of-the-art tools, which are designed for news text. And you can see that by using in-domain data, we're basically doing a lot better in each case. We've made these tools available online, so you can go download them and use them. And I should mention here, too, there's also other people like at CMU here working on these same kind of tools. And these are available as well. I think they're kind of all complementary, so definitely look into different options there as well. OK, so given that we now have access to these NLP tools, which are tuned to work on this noisy Twitter text, a natural question is, well, what can you actually do with that, right? So just to give one answer to this question, I've built a system which is automatically extracting a calendar of popular events coming up in the near future from Twitter. And so to do this, we're continuously processing a stream of about 2 million tweets per day using the NLP pipeline I just described. So this includes things like part-of-speech tagging, named entity recognition, and then we're also extracting and resolving temporal expressions. So for example, if we see a phrase like next Friday, we can actually figure out the exact calendar day that's referring to, because we have the timestamp from when the tweet was written. OK, so then we can just count the number of times that each named entity co-occurs with a reference to each date, and then plot the most strongly associated named entities for each day on a calendar. And so here I can show a quick demo of this. Right, so here you can see, so today is the 7th, I guess, right? So if we look ahead to, let's see, Saturday, the 12th, you can see there's a lot of people talking about something to do with Monsanto. So we can actually click on that to drill down and get some more details here. So here I'm basically just showing all the tweets which mention Monsanto in addition to a reference to October 12th. And you can see basically there, people are talking about this, march against Monsanto. It's like a protest event, something to do with Monsanto that's planned for this coming Saturday. And then just a couple of other examples here. So next Monday, there's basically a rumor that Apple's going to announce a new version of the iPad. And then on next Wednesday, Ubuntu has a new smartphone operating system, which is scheduled to launch. And so there's a lot of stuff on here. And if you're interested to kind of see this and browse it, send me an email, and I can send you a link to this. OK. So right. So we were actually pretty surprised to see that this works so well. So if you try to do the same kind of thing in newspaper articles, it's actually a pretty difficult task. And so just to give some intuition for why that is, for example, to figure out when the bomb attack mentioned in the first sentence here, if we want to know when that takes place, we have to be able to figure out that the blast in the second sentence is referring to the same event, and also that the blast happened on Saturday, right? OK, so to make this even more complicated, we also have to recognize that this other bomb attack mentioned later in the article is referring to a totally separate event which took place on a different day. And so basically what's going on here is we have to solve these discourse processing tasks to kind of link information together across sentences. And these are some of the more difficult and I would say kind of unsolved problems in NLP. We don't know how to do this as well as we know how to take an individual sentence and kind of extract its meaning. OK, so in contrast, on Twitter, people tend to state things in a really simple, compact way. And so to give some kind of explanation for this, if you imagine a user writing a message on Twitter, they sort of assume that it's going to get mixed up in the feeds of all their followers. So they don't assume any discourse context that it's going to be understood in. In contrast, a sentence in a news article is really meant to be understood within the entire context of the article. So there's a tendency for information to get spread across sentences with the assumption that you can link it all together. OK, so the point to take away here is that by working with these short, informal messages on Twitter, we're able to sidestep some of these complicated discourse processing issues. OK, so given that we have this calendar of open domain events we're extracting from Twitter, a natural question for us was whether we can automatically categorize them into high-level categories, like sporting events, political events, product releases, and so on. And so this categorization of events into types would have a number of benefits. Probably the most obvious thing is it would just allow users to browse more customized calendars which match their interests. So there's a number of challenges that come up when we look at categorizing events on Twitter. So the main thing here is there's just a huge number of different types of events people can talk about. So people on Twitter can talk about just about anything. And in advance, we're not even really sure what the right set of types should be. So even worse, the set of important types might actually change over time as new things become popular, more or less popular. Or if we want to focus in on a specific group of users, there might be a different set of event categories which best describe that data. So to address these challenges, we're proposing an unsupervised approach to event type induction, which is based on latent variable models. And so this approach has a number of advantages. It's able to automatically discover an appropriate set of event types which match the data. We don't need to annotate any individual events in advance, which of course is expensive and time-consuming. And we don't even need to commit to a specific set of event categories in advance. The model just kind of discovers the right set of categories from the data. OK, so at a high level, how these generative probabilistic models work is we make up a story about how our data was generated, which involves hidden variables and probabilities. And then, given some fixed data set, we're going to apply Bayesian inference techniques to infer values for the hidden variables, which will then tell us what the event types are and also the type of each event in context. OK, so I'm just going to walk through sort of a high-level explanation of the generative story for our model here, just to make it clear what's going on. So to start out, we'll group together all of the tweets which mention the same event phrase. So in this case, the phrase announce. And then we're going to have a set of types. And so each type is going to have an associated probability distribution over named entities that occur in events of that type. So we might have like a product release type, which assigns high probability to entities like Microsoft, Samsung, and iPhone, and similarly a type for politics and sports. OK, so now each event phrase, like announce here, is going to have a associated distribution over these types. So for, an announcement, for example, could be related to either a product release, a political event, or a sports event. OK, so now to generate the named entities in our data, we're just going to repeatedly draw types from this distribution. And then for each type we draw, we're going to draw a named entity from the associated type distribution. OK, and so just to be clear here, this is, again, just a description of the generative story. In practice, we're going to apply Bayesian inference techniques, which will then tell us what are the types, and also what's the type of each event in context. OK, so to run inference here, we gathered about 65 million of these entity event date tuples, which are basically just the same thing we were showing on the calendar. And for inference, we use collapsed Gibbs sampling, which is a pretty standard approach to inference in these type of models. In practice, we actually use this parallelized approach to Gibbs sampling. And so I should mention here that Gibbs sampling is really an inherently sequential procedure. But there's some theory that explains that the parallelization can be understood as an approximation to Gibbs sampling, which is already approximate inference. But we actually found this works pretty well in practice, and it lets us scale up to much larger data sets. OK, so here are some examples of event types which were automatically discovered by our model. And I should mention that the labels on the left here are just kind of my interpretation of the types. These aren't output from the model, but it's just to kind of make it easier to look at this figure. But I think you can see we have a pretty nice like sporting event here at the top, where we're seeing event phrases like tailgate, scrimmage, homecoming, and regular season. And then for entities, we're seeing things like ESPN, NCAA, Tigers, and Eagles. And then we also have like a nice TV event here where we're seeing phrases like new season, season finale, new episode, and entities like Jersey Shore, True Blood, and Glee, and then TV networks like HBO. OK, so we also did an evaluation to see how well our model can actually categorize events in context. And so I guess the takeaway here is that by using large amounts of unlabeled data, we're actually able to do a better job at this than a supervised baseline. Yeah.
How are the event phrases defined?
So it's kind of similar to the time bank corpus. So I basically just annotated a bunch of tweets following guidelines similar to the time bank corpus, and then train a CRF to extract the event phrases. Yeah.
Absolutely. So you said there were 100 event types?
Yeah.
About what percentage were actually?
Yeah, that's a good question. So I think it was about half of them sort of corresponded to meaningful event types. I think this is pretty similar with any kind of topic modeling. Typically about half the topics are useful and half are kind of not. OK, so so I just talked about this sort of unsupervised approach to information extraction, which I think has a number of benefits. It lets us scale up to large data sets. We don't need to specify the categories in advance. The model sort of automatically discovers what are the right set of categories to match the data. But I think there's an interesting question, which is, what should we do in the situation where we have access to large structured data sets, like Freebase's Wikipedia? Can we sort of use these as a distant source of supervision? OK, and so this actually is the case for this named entity categorization task, which I'm going to move on and talk about now. So it's really easy to get large lists of named entities and their types from these structured data sources. OK, so there's a number of challenges that come up when we look at categorizing named entities on Twitter. So again, there's a huge number of different types. So people are talking about bands, movies, products, and so on. And many of these types are relatively infrequent. So even in a really large, manually annotated data set, there's going to be few examples of these infrequent types to learn from. Okay, so I think because of this, we can't simply rely on supervised learning alone here. Okay, so the second problem is that tweets are often very terse. So they often simply just don't contain enough context to tell what type of entity they're referring to. So for example, in this case, it's really hard to know what type of entity KKTNY is referring to without some kind of additional background knowledge. Okay, so to address these challenges, we're proposing a weakly supervised approach to named entity categorization, which uses large lists of named entities and their types we've gathered from FreeBase. So of course, we can't just look up a named entity to figure out what its type is. So for example, if we look up China in FreeBase, we see that it could be either a country or there's a band called China. There's a number of different people whose name is China. So we really need some way to disambiguate between these different possibilities, because the FreeBase dictionaries are really ambiguous. Okay, so to do that, we're proposing an approach based on constrained topic models. And so the idea here is to use the FreeBase dictionaries to generate constraints in the model. And so I think to kind of explain this, I'll just walk through the generative story again. So basically what's going on here is, again, we're grouping together a bunch of tweets. So in this case, we're grouping together all the tweets which mention the same named entity instead of the same event phrase. So in this case, JFK. And then we're going to have a set of named entity types. And each entity type is going to have an associated probability distribution over words which co-occur in context with that type of entity. Okay, and so again, so each named entity will have a distribution over these types. But the key difference here is that these type distributions are going to be constrained based on the FreeBase dictionaries. So for example, if we look up JFK in FreeBase, we might see that it could refer to either a person or an airport, and then we'll constrain these type distributions based on those two possibilities. Okay, so then to generate the context words in our data, again, we'll repeatedly draw types from this distribution and then generate the words based on the associated type distributions. And again, this is just describing the generative story for our data. In practice, we'll apply Bayesian inference techniques, which will tell us the type of each named entity in context. Okay, so just to show that this model is actually doing something useful, here I'm showing some example type lists, which are automatically generated. So for each type here, I'm showing the top 20 entities predicted by our model, which weren't found by FreeBase. Okay, and so I should also mention this is like for sort of 3 out of the 10 types, and these are some of the more difficult categories. So the easy ones are things like person and location. So for example, for products, we're seeing things like Nintendo DS Lite, Apple iPod, iPod Nano, and so there are some segmentation errors mixed in here as well. But I think what's really cool is that we're actually able to correctly categorize some of these Twitter-specific abbreviations, which you just wouldn't be able you just wouldn't have them in FreeBase to begin with. So for example, it's able to figure out that KKTNY is a type of TV show. Okay, so right, so again, we evaluated the ability of our model to actually categorize named entities in context. And so here I'm showing our performance compared against a bunch of baselines, including a supervised baseline, which actually does really well on the more frequent categories like person and location, but does quite poorly on the cases where there's few examples in the training data. And then we also compared against the co-training approach to weakly supervised named entity categorization proposed by Collins and Singer, and we're actually doing quite a bit better here. Okay, so why is it that LDA is winning here? So I think there's a couple of reasons for this. So first of all, it's able to share information about an entity's type across mentions. And so this is really helpful in these ambiguous cases where there just isn't enough context to figure out what type of entity is being referred to. And then the other thing is that by using the FreeBase dictionaries as constraints, we're able to just better leverage this highly ambiguous source of training data, rather than relying on only the unambiguous cases for training. Okay, so I just talked about this new approach to distance supervision, which is based on topic models and is appropriate for the situation of highly ambiguous training data. So there was sort of a natural question that came up while we were looking at this, and that is, what happens in the situation where there's some information missing from the database? And so the answer to that is this leads to errors in the training data. And this is a really general problem that affects distance supervision, both for this weakly supervised named entity categorization task and also the more common application of binary relation extraction. OK, so I'm going to move on and talk about extracting binary relations now. And so it turns out that for relation extraction, people typically use a lot of highly engineered features, which are often correlated and overlapping. And so the generative models that I've been talking about so far are really not a good fit for this kind of data, because they make really strong independence assumptions about the features. So instead, at this point at the talk, I'm going to move on and start talking about conditionally trained models. OK, so this is kind of a high-level picture for what the setup looks like for distance supervision for extracting binary relations. So to start out with, we'll have a relation, in this case, the born-in relation. And then FreeBase is going to give us a large list of people in the locations where they were born. OK, so then for each pair of entities here, we can go search in a large text corpus to find sentences that mention the entity pair. OK, so now we can just extract features from these sentences and treat them like labeled training examples for a supervised classifier to predict new instances of the born-in relation. OK, so the question here is, what happens if there's some information missing from FreeBase? So what if this pair, Barack Obama and Honolulu, happen to be missing? So now all of these sentences are now functioning like negative training examples for the born-in relation. And I think you can see this is going to be a problem. OK, so before I get into how we're going to address this, I'd like to just walk through a model for distance supervision in the context of binary relations. And this is some work due to Raphael Hoffman and others at the University of Washington. OK, so to start out with, we'll have a pair of entities, Barack Obama and Honolulu. And then we're going to get to observe all of the sentences in our corpus which mention that entity pair. OK, so now we'll have a classifier which is going to predict for each sentence which relation it mentions between Barack Obama and Honolulu. And so unlike the standard supervised learning setup, we don't get to actually observe these variables during training. Instead, we only get to see these aggregate level variables we get from FreeBase, which tell us, for example, that he was born in Honolulu and he lived in Honolulu. OK, so of course, the question here is, how do we relate these aggregate level variables to the sentence level relation mention variables? And so one answer to this question is a simple deterministic OR function. And so basically what this is saying is, if at least one sentence mentions that Barack Obama was born in Honolulu, then that fact is true in aggregate. If none of the sentences mention that fact, then it's false. Conversely, if FreeBase says that Barack Obama was born in Honolulu, then we have to extract it from at least one sentence. OK, and so to tune the parameters of this model, we just maximize the conditional likelihood of the observed facts in FreeBase conditioned on the observed sentences. OK, so for learning here, we're taking an approach based on the structured perceptron, which is just an iterative gradient-based update to the weights. And in addition, we're taking an online approach to learning, which just means we update the parameters after seeing each entity pair rather than going through all the data and doing batch updates. OK, so this is what the gradient looks like. It's just the difference between these two expectations over the features. So in practice, these expectations are too difficult for us to compute. So instead, we're approximating them with maximizations. So basically, we have two inference problems here. So we need to be able to find the best assignment to the sentence-level hidden variables conditioned on the observed facts from FreeBase and the sentences we've seen. And then we also need to find the best assignment to the sentence-level variables just ignoring FreeBase. OK, and so this unconstrained inference problem is actually trivial to solve. The constrained problem is a little bit more complicated, but it turns out that it reduces to a weighted edge cover problem that we can solve exactly in polynomial time. OK, so there's two assumptions that are being made here during learning. So the first is that if a fact isn't found in FreeBase, we can't extract it from the text. If a fact is found in FreeBase, then we have to extract it from at least one sentence. OK, so these assumptions are good because they're driving the learning. But in the situation where there's some information missing in either FreeBase or in the text, these lead to errors in the training data. Okay, so how might we change this model to better handle the situation of missing data? So what we're proposing to do here is to take these aggregate level variables and split them into two parts. One which represents whether a fact is mentioned in the text, and the other which represents whether it's mentioned in the database. Okay, and so then these factors between the two new variables are just going to encourage but not require that they agree with each other. So I think now you can see that the facts in FreeBase are acting more like soft constraints as opposed to hard constraints like before. So for example, now it's possible to extract a fact that's not in FreeBase if the local sentence classifier is highly confident, but we're going to have to pay some penalty for doing that. Okay, so the learning is pretty much the same as before. So the only difference here is that we're now maximizing over these new aggregate level hidden variables that we've introduced. So this doesn't actually really make any difference for the unconstrained inference problem, but the constrained inference problem no longer reduces to this weighted edge cover problem like before. So we need to figure out some way to deal with the inference here. Okay, so the problem that we're trying to solve is, again, given the observed facts in FreeBase and sentences we see in the text, can we find the best assignment to the sentence level relation mention variables? And you can view this kind of like an optimization problem with soft constraints. Okay, so to make kind of a long story short here, we basically found that using local search almost always finds an optimal solution. And there's kind of a, so this local search works well as long as we use a carefully chosen set of search operators, which I won't kind of go into detail on. But we kind of explored a number of different inference strategies here, including A*, which is guaranteed to find an exact solution, but of course it's time and memory intensive. But basically, using A*, we can show that this local search approach, like in over 100,000 problems from our actual data, it only missed an optimal solution in 3 cases. So this is nice because it's fast and almost always exact. Okay, so of course the real question here is how does this affect performance in terms of precision and recall, which are the things we actually care about. So here I'm showing precision and recall curves on the sentence level relation extraction task. And so the the red curve here is the system which is using hard constraints. So that's sort of like the baseline. By just relaxing those as soft constraints and setting 2 handset parameters in the model, we're able to get the black curve, which is a huge improvement. And then by incorporating additional side information in the form of a missing data model, we're able to do even better, which is the green curve. Okay, so I'd like to just pause for a minute here and summarize what I've talked about so far. So I presented an analysis of challenges that come up when we look at extracting information from informal text. I talked about our NLP tools we've adapted to Twitter, and these are available online. I also showed this demonstration of a system which is automatically extracting a calendar of popular events coming up in the near future. And then I presented 3 different probabilistic models for open domain information extraction, including an unsupervised approach to event type categorization, a new approach to distant supervision using topic models, and then I also talked about some recent work on modeling missing data and distant supervision. Okay, so I've also done some work on other things other than information extraction too. So I've done some work on modeling conversations in social media. So I think we're in a pretty exciting position right now. We have access to like huge amounts of naturally occurring conversations, and there's an interesting question of how we can use those to build conversation models from data. And so I'll just talk about one example of this really briefly here. Oh, I guess the food's here. Should I stop or? Okay, sure. Yeah, I'm almost done, I guess, anyway. So, okay, so right. So one example of this is we've applied some techniques from statistical machine translation to automatically generating replies to Twitter status messages. So in SMT, the task is given some foreign text, we want to be able to translate it into English. And in order to learn a model to do that, we have access to large parallel corpora of paired foreign and English sentences. And so the idea here is that this response generation task is actually kind of similar in some sense. So our goal here is to, given an arbitrary user utterance, we want to be able to generate an appropriate reply to that. And the question is, can we learn to do that using a large corpora of naturally occurring conversations we've gathered from Twitter? OK, so at a high level, how phrase-based translation works is, we take the input sentence and segment it into phrases. And then for each phrase in the input, we translate it into a phrase in the response, potentially with some reordering. And to generate a good response here, we want both a high sort of translation score, so we want good translations, and then we also want a good score according to the language model, which sort of ensures that the response is fluent. And so this is actually like output from our system here. And so you can see we're able to learn some of these kind of high-frequency response pairs, like for dinner is translating as yum, come over translates as be there, and who wants to translates as want to. OK, so and we have like a demo of this online too. So you can check this out if you're interested. But if for example, I'm feeling sick translates is feel better soon. And this is kind of like n best output, right? So these are all different possible ways to reply. OK, so this is kind of a cute demo and stuff, but I think there's actually some useful applications here as well. So one thing would be conversationally aware predictive text entry. So imagine that a user just sort of sent you a text message, or your friend just sent you a text message, and you're typing a response to it using some noisy input mechanism. Well, I think we can actually do a better job of predicting what you're trying to type by taking the message you just received into account. So for example, if your friend texts you that they're feeling sick, we should be able to do a good job of predicting how you'd reply without even seeing any input from the user. OK, and then I've also done some work on paraphrasing between language styles. And this is in collaboration with some folks at New York University. And so just to highlight, again, one thing here. So we basically looked at paraphrasing Shakespeare's plays into modern English and vice versa. And so to do that, we've basically collected a lot of parallel text of like sort of modern translations of Shakespeare's plays, which we can then use to build models to sort of do translation in both direction here. And so then one cool thing we can do is take sort of modern movies and translate them into Shakespearean style. So for example here, if you'll not be turned, you'll be destroyed, gets translated as if you'll not be turned, you'll be undone. And Father, please help me is translated as Father, I pray you help me. OK, and so we have a demo of this online as well too. OK, and again, this is kind of a cute application, but I think there's actually useful things here as well. So one thing would be just, so there's only modern translations for 17 out of Shakespeare's 38 plays. So by automatically translating the other plays, maybe we can actually make them more available to students, which could serve some kind of benefit. And then, of course, there's a lot of other authors from the same time period as well. And then I'm also interested in looking at other domains in this sort of stylistic paraphrasing task. For example, maybe like paraphrasing technical documents into sort of easily understandable English, and paraphrasing between formal and informal texts, which I think other people here are looking at as well. OK, so I guess I was going to wrap up. I'd just like to thank my collaborators, and thanks for coming to the talk. Yeah.
I've got a quick question. What are your thoughts on how to model or deal with deception in text? Things like advertising campaigns or something that,
Yeah, no, this is a great question. And I think it's definitely relevant to the Twitter extraction stuff. So you'll see a lot of, I mean, I'm not sure so much about deception. I haven't thought about this. But you'll definitely see sort of like conflicting information, especially relating to things like the Apple releases, right? Like you'll see often like multiple different dates people are mentioning for when the new iPhone's coming out as like rumors kind of like, yeah. So like kind of how can you deal with that and figure out like what's the most up-to-date information is one interesting thing I'd like to look at. But yeah, deception actually is, seems like another interesting direction in itself. I don't know.
Within the Bayesian framework, though, could you have like a confidence interval on, say, like these events or something?
Yeah, that's a good question. Yeah, I mean, I think all the models that I'm talking about so far just kind of assume that what's said is just truthful, Yeah. So I'm not, I mean, I guess if you start thinking about the users and how believable they are, that gets into a whole different area of like, I mean, I think it sounds really interesting, but it's not something I've really put a lot of thought into. But yeah.
It's like Twitter versus newspapers,
Yeah, that might.
It's a major factor.
Yeah, that might be some way to get at it. Is sort of like if you take newspapers as ground truth and see like how does information people are saying in Twitter correlate with it. You know, could be interesting.
So you started off talking about the fact that people do all sorts of weird things with orthography and spelling and all that on Twitter. And you solved that in your supervised pipeline, kind of ran behind all of this. What about recognizing that there are maybe 10 different spellings of Obama or something in the later models when you're rather than having just 10 different entries in your probability table?
Totally. Yeah, no, I think this kind of problem of co-reference is something we're not dealing with at all. For us, an entity is just a string.
Yeah.
I think that's totally interesting area for future work, doing sort of like entity co-reference, entity linking, and like event co-reference. It's not something I've really looked at.
Yeah, I mean, I guess just sort of what do you think the right solution is? Is it going to be something like where you first canonicalize the entities, or do you need to, is this all going to be one big global model where you're reason about that jointly?
That's a great question. Yeah, I mean, I think like doing it jointly sounds really interesting. I guess then the question of like how do you do the inference efficiently? That's kind of, so most of the stuff I'm doing is pipelined, right? So we do this supervised stuff and then do a bunch of unsupervised learning on top of it. The main motivation for that, I think, is just efficient inference, right? But I think thinking about how to do it jointly, how to do it efficiently jointly, these are all really interesting areas for future work, yeah. Oh, yeah.
In your learning update using this gradient,
Yeah.
so you replace the expectation with maximum. So isn't it introduce some bias? Actually, why you don't just do some MCMC?
Yeah, right. Yeah, you could imagine doing sampling as part of the update or something. Yeah, I think this would be interesting. Yeah, I mean, I haven't tried doing that, but that was something that we were kind of thinking about. But
Because in low noise, actually, so maximum just approximates the expected very good approximation. But if you have if you have a very stochastic model, then actually maybe it's better to. It is a little bit more computational intensive, but you can generate samples using MCMC, and so it shouldn't be very bad. I mean, it's much better than
Totally.
the expectation.
Yeah, I mean, I think it's an empirical question. Is it sort of like just doing more iterations is better or getting more accurate gradients is better? It's a great question. Yeah.
I think it also speaks to sort of how multimodal you think the distribution is, right?
Right.
If you show these n-best that they're all synonyms or synonymous with each other, or are they two very distinct sort of ideas? If it is sort of multimodal, then you might not want to do it.
Right. Yeah, that makes sense. Yeah. Oh, yeah.
The missing data model where you split the T's and the Z's. So I'm thinking about how you modeled the case where you could predict something that was not in freebase. So was it the T's had like a none of the above type of value?
Let's see. So right, so like here basically, right, so if you predict something that's not in freebase, right, so then basically you're saying like, so let's say I predict Barack Obama was born in Honolulu, but it wasn't in freebase. I mean, that's not a good example because that's probably in freebase, but for some less prominent entity, right? So basically, if I predict that this fact that's not in freebase, then the corresponding relation is going to turn on because this is a deterministic OR. So it's basically if any of these mentions that Barack Obama was born in Honolulu, then that is going to be on just deterministically, right? And then we have these factors. So then we have the sort of observed fact that it isn't in freebase here. So these two kind of disagree with each other. And then we have this sort of factor here that just encourages disagreement. So it's basically like a penalty for like disagreeing with freebase, right?
I was thinking of the case where you predict something that's not in freebase.
Yeah.
So like it's not kind of like covered by this.
Yeah. So that's right. So basically, so if it's not in freebase, you can think of the value of this variable as 0, right? And then if we predicted it, the value of this variable is 1. So now they disagree, and you have to pay a penalty, basically, right?
I'm curious about how the big or affects. I mean, you would think the more times you see something in the data, the more likely it is in freebase.
Yeah, no, that's a great question.
Thrown away by the model, or does it
I think it kind of comes out naturally in the posterior inference. So if there's like a lot of local classifiers here that want to predict that Barack Obama was born in Honolulu, then you're basically going to have a harder time saying that that isn't true, right? Do you see what I mean? So it's like if you say, if you want to, basically, if you say it's not true, you get some, benefit from like this factor, right? But if there's like a bunch of other factors that would have sort of higher score that outweigh that, right? Yeah, no, that's a great question.
Again, on the deterministic OR, what about extraction errors?
Yeah.
Is there any mechanism for saying that sometimes my extractor is just wrong?
That's a good question. Yeah, so this is all during training too, that this is even coming into play, right? So, but yeah, no, it's interesting to think about extractor errors and how that would fit into this. Yeah, you could think about using something other than a deterministic OR here, like a noisy OR, or like, even just some kind of a linear combination. We didn't try doing that, so I haven't done any experiments to say that this is better than the deterministic OR, but it's a great question. Yeah.
And I guess it'd be similar to if some of your sentences are just wrong.
Yeah. Yeah.
Like some Ritter article that says
yeah.
it's not one of them.
Totally, yeah. So that's kind of an assumption that's baked into the model, is that the only thing we're seeing is like the truth, right? And I don't know. You have to make some assumptions, right?
If you change the deterministic OR to a noisy OR, would that make inference harder?
That's a great question. I think it would probably. I don't know. I'd need to think about it more. I'm not sure off the top of my head.
Okay, cool. Thank Alan again.
Thanks.